Good morning, dear students. Yesterday we have seen that the conductivity is not so useful term because it changes. Let us redefine conductivity. Conductivity of a solution is the conductance offered by a solution of length 1 unit and 1 unit cross section area. Here the cross section area is of electrodes. So the solution which is put between, you can see here, this is the solution. This solution with any concentration or any quantity of solid is kept in between the 1 centimeter cube area where two electrodes are placed about 1 centimeter, and this electrode have also the cross section area of 1 centimeter square. So these are the electrodes with 1 unit cross section area, and this is the constant. This length is 1 centimeter or 1 unit. Both the electrodes are placed 1 unit apart, and the quantity of solute is not fixed. The conductivity offered by this solution is known as 1 kappa or conductivity. So the conductance offered by this solution is known as 1 kappa, which is known as conductivity. Here I should write conductance. As the conductivity of solution varies with various as the conductivity of solution with various electrolyte in the same solvent differs due to ionic charge of ions which are dissociated, ionic size of ions which are dissociated, and the ability of these ions to move under electric gradients. Thus the conductivity term is not so useful. This is what we have studied into the last period. More meaningful term or more meaningful quantity or more meaningful physical quantity introduced, and this physical quantity which is introduced is known as the molar conductivity. So now let us try to study what is molar conductivity. Molar conductivity lambda m is defined as the conductance of the electrolytic solution kept between electrodes of a conductivity cell at a unit distance, but having a cross section area large enough to accommodate sufficient volume of solution that contain 1 mole of electrolyte. Here, my dear students, the the electrode must be placed 1 unit distance apart, but that cross section area can be any large cross section area that accommodate the volume of solution. In this volume of solution, it is necessary that we must have added 1 mole of solute. So this is what it is, the requirement for the conductivity, which is known as the molar conductivity. Here cross section area must be 1 unit. The solution must contain 1 mole of solute and must not be 1 unit. Here the cross section area must not be 1 unit. So in case of molar conductivity, the cross section area of electrode must not be 1 unit. It should be the large enough to accommodate the any volume of solution that is containing the 1 mole of solute, and the solution must contain 1 mole of solute. This is even necessary. The quantity is fixed here. So now we'll arrange like two electrodes large enough to accommodate any volume that contain 1 mole of solute, and this is the solution that contain 1 mole of solute. So now if we measure the conductivity here, it will be considered as a molar conductivity. You can see that this solution is placed in 1 unit distance. When we look at both the figures, we have same volume of solution. You can see that this is the solution that also is 1 centimeter cube. When you look at this figure, the volume we consider as a 1 centimeter cube. When we look at both the figures, we have same volume of solution, but the quantity of solute is different. But still, in this case, we can say that lambda m, that is molar conductivity, is equal to conductivity kappa. Now I will write this kappa as a kappa 3, my dear student. Now we will do some extra arrangement, or we will study the same two conductivity cell in a different perspective. Now what do we do? We would add water to both the solution. Both the solution have 1 mole of solute. It means we would do dilution. Now what do? We arrange one more electrolytic cell. This in this electrolytic cell we have added 1 mole of 1 mole of substance. This electrolytic cell we also have added 1 mole of substance. This electrolytic cell has this electrode with the cross section area 1 unit square, that is 1 centimeter square. This electrode also we have put the cross section area 1 centimeter square, and it is large enough. Then what did we do in this solution? As we have the 1 mole of substance, only for this the conductivity measured is known as 1 kappa. Now what happens? We add 9 unit volume of 9 unit volume of water. Let us say 9 centimeter square or 9 ml. So total volume turns into 10 ml, and the amount of solute is 1 mole. Here also the total, we have added 9 ml of water. The amount of solute is again 1 mole. So only 1 mole substance is dissolved, and we measure the conductivity, which is now is considered as a molar conductivity. So here the molar conductivity is lambda m, which is same as the volume has been increased, but we have this electrode large enough to accommodate this volume, and whatever the conductivity offered by this solution of 10 ml is known as 1 molar conductivity. But this kappa depends upon the volume of the solution. So as the volume has turned 10 times, the kappa this time has become as 10 kappa. This is what it is known as the 10 kappa 2. As the volume of solution increases and both the solution have 1 mole solute, conductivity become 10 kappa 2. Kappa 3 is equal to lambda m initially. So now kappa 3 is equal to 10 kappa 2. That means kappa 3 minus 10 is equal to K2. It means that on dilution, the value of kappa conductivity changes, and now as we have added 9 unit volume of water, the final kappa 2 is equal to the initial kappa by 10. So this conductivity is decreased 10 time if the volume is increased 10 time. So on dilution the conductivity decreases, but molar conductivity lambda m remains same, because this 10 ml of solution contain 1 mole of solute, or 1 mole of solute will always give you molar conductivity irrespective of whatever the total volume of solution is available. Solution has 1 mole of solute, that is why this conductivity offered by this cell is known as molar conductivity. Now suppose instead of 9 ml or 9 volume of solution, we would have added 999 volume of water. What happens? Total volume turns into 1000 volume. Let us say 1000 centimeters square, that means centimeter cube, that means let us say it is 1000 ml. So concentration is 1 mole per liter or 1 molar. Now conductivity would be 10,000 kappa. Now this 10,000 kappa, that means kappa is equal to K3 by 10,000. That means if we add 999 volume of water, the final conductivity is equal to 1 by 10,000 the initial conductivity. So again conductivity decreases, but molar conductivity remains the same lambda m, because the solution still has 1 mole of solute, and they have electrode large enough to accommodate the volume, this 1000 ml or 1 liter volume of solution. So here your lambda m is equal to kappa into 1000, as I have written here. That is divided by 1. My dear student, 1 here represents, here in the denominator it is necessary to write 1. 1 here represents 1 molar or 1 mole per liter concentration. If the concentration is 0.02 molar, that means 0.2 mole of solution in 1000 ml, then lambda m would be kappa into 1000 divided by 0.2. If the concentration is 2 molar, that means 2 mole of solute is dissolved in 1 liter of solution, then lambda m is equal to kappa into 1000 divided by 2. So provided the unit of kappa is Siemens in centimeter, here the unit of kappa must be Siemens per centimeter, because 1 centimeter cube is equal to 1 ml and 1000 centimeter cube is equal to 1 liter. So here in general what we can write, lambda m is equal to kappa multiplied by 1000 divided by C. Remember my dear students that kappa must be in Siemens per centimeter and C must be in mole per liter, and 1 liter, that is your 1000 centimeter meter cube or 1000 ml. That means the concentration C must be mole per 1000 centimeter cube or mole per 1000 ml, where C is mole per liter concentration of the solution. If the unit of kappa is Siemens per meter and C is in the mole per meter cube, then we will write lambda m is equal to K by C. Remember my dear students, here there is no need to multiply kappa with 1000, because the concentration C is written in mole per meter cube. That means mole per 10 to the power 6 centimeter cube, because 1000 liter is equal to 1 meter cube, and 1000 into 1000 centimeter cube is equal to 1 meter cube. So this 1000 again come back as a denominator of this centimeter cube, and this centimeter cube turns into 10 to the power 6 centimeter cube. So here we need not to write 1000, my dear student, because the unit of kappa is already Siemens per meter. Now we'll understand the units of molar conductivity. The unit of molar conductivity is Siemens meter square per mole or Siemens centimeter square per mole. How do we get this? Let us try to understand. See, when the concentration, when the value of the unit of kappa is Siemens per centimeter, the concentration that we take is mole per 1000 centimeter cube. That is 1000 ml. This is nothing but your 1000 ml or 1 liter. This 1000 and this 1000 simply turns into, this is Siemens per centimeter cube mole. This centimeter cube goes up, so it turns at Siemens per centimeter multiplied by centimeter cube into mole. This centimeter inverse multiplied by centimeter cube turns into centimeter square, and we get one of the unit as Siemens centimeter square per mole. Now if we take kappa divided by C, so here we always know that the unit of kappa must be Siemens per meter, and this is mole per meter cube. This denominator of denominator turns numerator, so it is Siemens per meter multiplied by meter cube per mole, and that is why it is Siemens. This meter inverse multiplied by meter cube turns into meter inverse, and the unit is Siemens meter square per mole. Now how we interconvert these units? So we'll understand the interconversion. 1 Siemens meter square per mole. Meter is 100 centimeter, so it is 1 Siemens into 100 centimeter square per mole. So it is 1 Siemens into uh, 10,000 centimeter square per mole, that is your 10,000 Siemens centimeter per mole, that is 10 to the power 4 Siemens centimeter per mole. Therefore 1 Siemens meter per mole is equal to 10 to the power 4 Siemens per Siemens. 1 Siemens into centimeter per mole, or 1 Siemens into meter square per mole, is equal to 10 to the power 4 Siemens into centimeter square per mole, and therefore 1 Siemens into centimeter square per mole is equal to 10 to the power minus 4 Siemens meter square per mole. So this is how we can understand the interconversion of the solution. Now we want to understand the effect of dilution. That is what we have already seen it, but just I want to give you repetition, because the same kind of question is asked into your textbook exercise. We have seen that when volume kept same, kappa is equal to lambda m. That is what we have written as kappa 3. Now what happens when diluted uh, by 9 volume of water or solvent? Lambda m is equal to 10 kappa. This is what we have written as 10 kappa 2. So when diluted by adding 999 volume, lambda m become 1000 kappa. So on dilution by keeping the quantity of solute the same, kappa changes, but lambda m remains the same. Let us understand it. Initially it was kappa 3, so kappa 3 was lambda m. Then it turns by adding 9 volume of solvent, kappa k3. Kappa 3 becomes is equal to kappa 2 into 10. Your kappa 3 is equal to lambda m. That means kappa 2 is equal to kappa 3 by 10. So by adding the 9 unit volume of solvent, the conductivity is decreased by 10, or become 1/10 of the initial conductivity. On dilution with 9 unit volume, the final conductivity is equal to 1 by 10 the initial conductivity. On dilution with 919 unit of volume, the final conductivity kappa is equal to 1 by 1000 the initial conductivity, that is kappa 3. So final conductivity is 1000th the initial conductivity. Thus we can easily understand that on dilution conductivity kappa decreases, but the molar conductivity remains the same, because the quantity of solute, that is 1 mole, is kept constant in, and that is 1 mole. So my dear students, this is the answer of your exercise question 3.7. Please keep in your mind. Thank you, dear student.